My name is Michelle, and I'm an engineer at Google, and I'll be talking about local persistent storage today and give an update. First, I'm going to just give some background information and motivation on the project. Then I'll talk about what we have done in 1.7 and 1.8. I'll talk about what we're planning in 1.9, and at the end also talk about some of the future features on our roadmap. So first, to start off, why do people want to use local storage? There's two main reasons. One is for performance, in order to directly access local SSDs that might be on your host. As an alternative, you can use high performance network storage, but it also requires a lot of supporting infrastructure to support, and that also costs money. The second reason is to increase your hardware utilization in your data center. So, if you have all these disks sitting around, you want to be able to use them to their maximum potential to reduce your costs. But there are some downsides of local storage. So the first downside is that your data availability and durability are tied to the node and also to the underlying disks. So your application can face downtime if the node or the storage fails. And also potentially if your disk fails, you could have data loss as well. So as a result of that, your application placement is not flexible. Or sorry, another reason is that your application is not flexible. So you need to plan your resource usage more and be able to reserve specific resources on specific nodes. So for all those reasons, local storage is not meant to be a general purpose storage solution in Kubernetes, and it's only useful for some specialized use cases. And the major use cases that we are targeting are distributed file systems and data stores. So those kind of applications are fault tolerant to node failures because they inherently maintain replicas across multiple nodes and can handle nodes crashing or disks failing. And they are able to reconstruct the data from the remaining replicas. So examples of those kinds of applications are Cassandra, MongoDB, Cluster, Ceph. There's an endless list of all these sorts of different implementations available. The second use case that we're targeting is for large caches. So for these kind of use cases, even though they can handle losing the local data, they want to avoid it as much as possible because reloading all that data into the cache on a cold restart could be a big performance penalty and can also impact the application availability as well. So the current challenges of using, there are many current challenges of using local storage in Kubernetes today. They're kind of described in two main problems. The first is that the scheduler is not aware of local storage node constraints. So the Kubernetes scheduler today assumes that your workload can be scheduled on any node. It doesn't know that if you specify this local disk, that it actually has to go on a specific node. And the other problem is that the current mechanism to use local storage today is host path volumes, and host path volumes themselves have many downsides. First is that it has an unmanaged volume lifecycle. Kubernetes does not do anything about creating and deleting host path volumes. It's up to the users to create the volume and then clean it up when they're done with it. The second problem is that because you can specify the path in the pod, you have a lot of path collision issues. So you could have two pods specify the same or conflicting paths, and there's nothing the other application can do to stop the other path or the other pod from interfering. And kind of related to the same thing is that host path volumes kind of give your pod too many privileges because your pod can specify any path on the system. It can specify, a path to potentially corrupt the system's data if needed, or even access other people's volumes. So for that reason, many administrators end up disabling host path altogether. And if you are an application in that cluster that needs to use local volumes, and if host path is the only way there and your administrator disables it, then you're just out of luck. Another big problem with host path volumes is that the specification is not portable across clusters and environments, because you have to actually specify the path on that node. So in your application spec, you have to know what node you're going to run on, where your data is exactly on that node. And if you want to take your spec and run it into another environment, you need to, change the spec and update it every time you move it, which makes it harder to, share and write a general spec for your application to share with others. Because of all these issues, what people have had to do is to build manual schedulers, or they have to build custom schedulers and custom operators, custom management solutions in order to work around all of these. And it has a lot of impact on the user. So it becomes a high barrier to entry, because if you want to use local volumes, you have to do all this extra work to manage the scheduling and to manage the disks. So, a lot of people, they just end up deciding not to run their stateful workloads on Kubernetes and, just run it outside and manage it as a separate service. What that means is that you won't be able to use Kubernetes as a single control plane to deploy and scale your applications, all your applications. At the same time, you get reduced application developer velocity, because now you have to spend more time building up all this infrastructure and less time building your application. And the third problem is that you won't be able to leverage many of the powerful features that Kubernetes offers, including horizontal scaling, advanced scheduling, and also the whole portability part of being able to move your workloads anywhere. So those are the major problems that we're facing today. So we have two major goals in this project that will hopefully fix all of these issues. The two main goals: first goal is to expose local disks as persistent volumes. This is going to solve the portability problems, because we can use the abstraction of the persistent volume objects and the persistent volume claims. Once you can specify a local disk as a PV, then you can port your spec across clusters and different environments, and you can also easily switch between different storage providers through the storage class. So you can you can start developing your application using some remote disk storage, decide that you want better performance, and then you just easily switch over by storage class and use local disks instead. The other benefits of using the persistent volume object is that you can have a managed lifecycle. The persistent volumes has a clearly defined lifecycle, and you are able to you're able to provide isolation between pods. So if you make each disk a persistent volume, because you can only have one claim bind to a single volume, you can prevent the issue of multiple pods potentially colliding and using the same local disk. And also for security, there's a lot of benefits in terms of reducing the pod privileges. So the issue with host path was that you could specify any path on the system. But now, because persistent volumes can only be created by administrators with administrator privileges, it's up to the administrator to define which disks are available, not the pods. And then the second goal of the project is to make the scheduler aware of, oh yes.
So sorry, so the smallest, So the smallest local volume you can provision is a granularity of the disk. It's not smaller than disk.
You can provision smaller than a disk if you want. We don't enforce that it's a complete partition or not.
Okay.
Yeah, it's up to the administrator to decide if they want to provide dedicated whole partitions or whole disks, or if they want to provide just some shared path in a file system. Generally, at least for supporting the use cases of high performance databases and data stores, typically for guaranteed, or in reliable performance, you want to use dedicated disks, but it's not a requirement. Okay, so the second goal of this project is to make the scheduler aware of local disk placement constraints. If we can solve this problem, then applications won't have to write their own custom schedulers to handle scheduling their applications to the same nodes where their disks are located. And in addition to this, the benefit we'll get is that we will be able to integrate with all the other Kubernetes scheduling features. So you'll be able to use stateful sets to scale up and down your application. You can use the scheduler pod affinity and anti-affinity and node taints and tolerations, and basically everything. All the pod scheduling constraints will be considered along with the volumes topology constraints at the same time.
So I don't know if you can do it today or not, but is it possible to restrict the scheduling based on disks to a certain set of worker nodes? Or would you consider doing something like that? Could this mechanism be extended to do that?
Sorry, can you repeat that?
Yeah, so I have a remote storage. I'd like it to only be mapped into a certain set of the worker nodes. And I'd like the scheduler to be aware of that.
Yeah, so today we don't really have a way to do that. I think the only thing we have right now is we have this hard-coded label for zones. And if your persistent volume has that zone label, then it will restrict the nodes to the nodes with the same zone label.
Can't you do that with like taints, tolerances, or daemon sets, or labels in general?
Yeah, so that's restricting the pod. That's restricting the pod to certain nodes. But then but we're also saying the volume should also be restricted to those nodes.
I mean,
yeah,
isn't what you're asking for basically just defining your own topology? You're saying I have a zone that I want this to be available in?
Yes.
Yeah, and so that's something that we're planning to design for 1.9 is a more generic topology handling mechanism. Today, topology is hard-coded for cloud concepts, including region and zone for GCE and AWS. Essentially, what you're asking for is being able to define an availability segment for your storage system, and keep an eye out. There's going to be a design doc sometime in this quarter.
No, I'll post it in the meeting notes. Yeah. All right. So we've already started work on this in 1.7 and 1.8. We have our proposals here. We have basically 3 elements of the project. First is there's a new local volume plugin. It can only be used as a persistent volume, and for the alpha phase, we are only supporting file system volumes at the moment. So the local storage has to already be formatted with a file system on it. It can be a mount point or it could be a shared directory. The second part of the work that we've already done is we've added this new persistent volume node affinity. And we also have a matching scheduler predicate that will look for it. It's basically like a node selector on the volume object. So you can say something like this PV selects on nodes with the host name label equals to node 1. And the scheduler will look at the node affinity and reduce the set of nodes to what you specify in the selector. So for local disks, it's all reduced to one node, and you're basically saying this local PV can only be scheduled on this one node. And this is looking at, this scheduler predicate is looking at persistent volumes that are already bound. It doesn't handle the case where the initial case where you have a PVC that is not bound.
So how would you know which nodes have the volume? Like, how do you populate that information on a PV?
When you create the PV, you need to put it on. The administrator needs to specify it.
Okay, so let's say you're dealing with a data store that does its own replication.
Mm-hmm.
That logic is opaque to the Kubernetes.
Yeah.
How would you pass that information from, let's say, Cassandra or whatever data store you have to, because you don't necessarily know, for example, the replicas are on node A, B, and C. It might be, some other nodes.
Yeah. So when you create the persistent volume, you can say this volume is accessible from nodes A, B, and C. And then in your Cassandra pod, you'll have a PVC that binds to that persistent volume. And then in the scheduler, we'll dereference the claim to the volume and then figure out which nodes you can be scheduled on.
I guess my question is where Cassandra stores, or how are we doing, or some other arbitrary application, how it distributes the replicas. That part of it is not necessarily
so I mean,
visible to
the Cassandra replicas are not the PVs, right? Cassandra will use a local disk to store its replicas, but you're not creating a PV out of the replica. You're creating a PV out of the disk that Cassandra uses.
So the replica manager has to do the affinity.
Okay, so basically, this is not a means of limiting a pod to certain nodes where the data is, right?
This is
He's asking about data locality. Is this a way to enforce data locality?
you can, but so I don't know if Cassandra's a good example because Cassandra's not a file system and PVs are only file system based. We don't support object volumes so.
I guess the whole point of this is basically wherever your pod gets scheduled, you want your data to be there, right?
Yes. So the Cassandra instance uses a specific local disk. So that Cassandra instance always has to be scheduled to the node where that disk is. But Cassandra itself will manage what nodes the replicas are on. But then it's a different Cassandra instance managing the other nodes.
So I guess my question is, let's say Cassandra is managing 10 disks on 10 different nodes, right?
But you'll have 10 Cassandra instances, one running on each node, and the instance on each node will manage just its own local disk.
Okay. So it's not a single Cassandra instance managing?
No.
Okay.
So the reason I'm really, really excited about this feature is because for distributed data management platforms, right, they're all kind of the same in a way in that they, if you have a 10-node Cassandra instance, 10-node Mongo, 10-node HDFS, 10-node Gluster, 10-node Ceph, they're all the same in that you've got 10 nodes and each one's got its own local disk, right? And so the way I envision this making deploying distributed data management platforms awesome is this connects into stateful sets. So in stateful set, you have a volume claim template that you can specify a storage class. And so with each local PV, you add a storage class to each disk, right? So you could have potentially, if you say you had 100 nodes and each node had one disk on them, and you all had the same storage class, you say deploy me a 10 node Mongo cluster. It would go and look at the storage class, look at the pool of PVs, ascertain the local ones, and the scheduler would ensure that those Mongo pods only land on the nodes that have those local disks. And it just makes it magic, for deploying and scaling up as well, and failover. You can use taints and tolerations on this stuff. So like no execute if there's, a disk goes down and you don't want like network replication storms. So this is like the coolest thing ever.
So yeah, this goes beyond even storage. There might be some nodes which have better performance than other nodes, and so the node affinity thing in the PV is an extremely useful tool, and probably a can of worms, because what happens when the node is removed from the cluster? How hard is this affinity?
Yes,
And there are
it's very hard.
other questions around it. So is this available outside of the local storage? Like, can I use PV's node affinity for any kind of PV?
So at least in the alpha implementation, we put it under the local storage feature gate. But
Eventually it will.
you can always specify the local storage
Okay.
feature gate and put it on your own PVs.
Okay.
That's fine.
Awesome.
Yeah. So let's see. So that's the scheduler part. The third part is for the management of the local volumes on each disk. We've created an external static provisioner to manage the local disks. It's not a dynamic provisioner at this time. In the future, it might be. But basically, what it does is it manages the disk lifecycle. It runs as a daemon set, and then it will discover any local volumes that you've mounted into the local node, and it will go and automatically create persistent volumes for them. And then when the user ends up destroying those volumes or the claims, then it will go and clean up the data on the disks and then recreate them again for use. Okay, and then the last part of what we have implemented already is we just have a bunch of E2E tests running. It handles a bunch of positive test cases and negative test cases. It currently tests directory-based and mount-based local volumes and simultaneous mounts and also back-to-back mounts, and it tests the whole lifecycle.
So wait, these are running now?
Yes.
How much of this is checked in?
This is all checked in. This is 1.7 and 1.8. Yeah. Okay, so now I'm going to move on and talk about what we plan to do for this next release. Oh, wait. Before that, I have to talk about the problems with the alpha stuff. Okay. So there are a few use cases that currently don't work in the alpha implementation. The first issue is that persistent volume binding currently occurs before you schedule the pod. And because of that, we can't, when we bind a volume, we can't consider any of the pod scheduling requirements, like how much CPU or memory it needs, if it specifies affinity or anti-affinity, if there's any taints, we just completely ignore that. So it's very possible that we'll bind your claim to a volume on a node that your pod can't get scheduled on. This is actually a generic problem. It's not just, but it's just not a problem. It's not a problem with just local volumes. We have seen instances of this problem for zonal volumes as well. And then the second problem is that when we bind a volume, we evaluate it one persistent volume claim at a time. So there's no relation. If a pod specifies multiple claims, there's no relation between those claims. And it's very possible you can end up binding to, if you have two claims, each of those claims can bind to volumes on different nodes, which will make your pod not schedulable. This is also still a problem with zonal storage. We could end up provisioning 2 volumes in different zones, and you won't be able to schedule your pod. So these first 2 issues are generic issues for all PVs today, or zonal and local PVs today. The third issue is specific to local volumes. This is just, it's just because we don't have mount propagation at the moment, so we can't detect any new volumes that you've mounted after we've already started the provisioner. I think this shouldn't be too difficult to fix now that we have mount propagation. So, but just to be aware of the current limitations. Okay, so now I'll talk about what we plan on 1.9. I have lots of people helping me, which is awesome. So the first thing we're planning on doing for 1.9 is to enable raw block support for local volumes. This is primarily handled by Duraj, I guess. Yeah, do you want to come up and talk about it? I'm putting you on the spot, sorry.
So for raw block volume devices, some of the things that we did was use a soft link approach to allow a block to be discoverable under the same mount directory that a file system is discoverable on. The other thing that we had to worry about was cleaning. Cleaning in file systems is easy. You can do it by just doing an rm-r if it runs fast. Block volumes, it's a little harder. You need to run writes repeatedly over a large volume of data. So for that, we had to do an offline asynchronous volume deletion process. And the question was, what happens if the user gets impatient, deletes the persistent volume when it's still being cleaned? So for that purpose, we had to put in place locking mechanisms to ensure that when something is being cleaned, nothing else recreates a persistent volume for it. So logic like that has gone into it. So that's pretty much the essence of what you've done so far.
Cool. The other important aspect is that because there are so many different requirements on cleaning disks and different ways to do it depending on the hardware, there's no way we can just pick one method to support. So we've made it configurable, and you can write your own cleanup methods and specify them per storage class.
So a question: could cleaning take days, or
Yeah.
given if you have a big enough volume?
Potentially you could, but for reasonable size ones, it would be 4 to 6 hours. Especially if you're trying to zero out the volume entire space once, and then again do it with random values, and then again run a third attempt with a random value. It could take a while to go through each one of those cycles.
This is the reason we abandoned the recycler, right? We couldn't guarantee we could scrub consistently. Just there'd be dragons.
So it still feels like there's dragons. John, you grab a mic, but not me.
So from experience, we had this method inside of Cinder to do this exact thing, and we had to disable it because what we found was, particularly if you're using LVM, it will crash and it will lock up your system on a regular basis. There are ways to get around that, but you definitely need to be very careful and cognizant of some of the limitations that you're going to have. In particular, the resource usage and everything. If you don't throttle that and do things very explicitly, you're gonna crash your system and run into all kinds of problems.
So I think, as Michelle mentioned, one of the things we made sure was that it's highly configurable. Out of the gate, we're doing something very simple as far as cleaning goes. We just we create a new file system on top of it, and then we remove the signatures of the file system, effectively wiping out any previous file system that exists on that block device. So that's a very basic out of the gate option on cleaning. Beyond that, if an admin wants to do something more, maybe repeated rewrites, or maybe something very specific like HT param. They're free to then configure those different methods that suits the environment. So if you got an issue with LVMs, you probably wouldn't opt for one of these cleaning mechanisms.
So have we considered encrypting the block volume?
So I believe the HT param approach, behind the scenes, some of them implement it by, I think, encrypting and then throwing away.
Hardware that supports it.
Yeah.
But what about software?
We have not.
Flux or something like that. And do we have hooks in that would allow you to install the key whenever you make that PV available, right? Because that would kind of require both something at setup time as well as teardown, but it would fix the timing. Right?
So there's some problems to that. I mean,
Mike, is this going? Microphone?
Mike, what? Microphone. So I think the encryption idea is a really good idea. The problem is I think that opens up a whole nother set of issues and challenges and stuff like that, especially the key management piece. And I don't think we have anything to use as a key manager right now. So I think first solving the base general case like you guys have is probably good, and then having a configurable way to scrub it. You also might want to consider something like maybe you always use thin provisioning, LVM and thin provisioning, and then you don't have to worry about this anymore because the blocks aren't actually allocated, right? So I don't know if that works for you or not, but.
So I didn't quite get the thin provisioning part. I mean, even if you're thinly provisioned, once you kind of use up that storage,
you never. So the nice thing about thin provisioning is it never reallocates a used block. If you allocate a block that was used, it overwrites it. So you get the scrubbing for free, basically.
I see.
But then you'll run out of space. You'll eventually run out of blocks.
How do you mean?
Like if you just keep on creating volumes and destroying them, but you never reuse the blocks, you'll run out of space.
So thin provisioning will reuse the block, but when it reuses the block, it actually overwrites it. So it doesn't do like allocate 100 gig and just give you all of the available blocks without doing anything to it. It actually says, okay, here you have 100 blocks, but you don't actually have access to those blocks until you actually write to them.
Okay, yeah. So the nice thing about about putting the local disk management in an external provisioner is that people can use whatever method they want for their cluster. So if you want to use physical disks, then you can use that. If you want to use LVM, you can also use that. So it's all done externally, and you can basically plug and play to whatever your needs are.
Yeah, one last thing about the comment about using a software encryption. This is extensible. We're not hard-coded to a set of cleaning methods. You can introduce your own custom script. I guess the only limitation is that the custom script fires off and then it does its thing and it exits. So if anything has to happen after it fires off, any interactions that you need to do, that may not be possible. But if you got a set of params and you can fire off a script and make your cleaning happen, then that can be introduced.
And since it's external and configurable, like you said, I can point it to any device I want, right? So I could create a loops device, a DM crypt device, and just point your plugin to that and just use it. Is that true?
But I need to rotate the keys, right? So I need.
But you can do that.
Stuff at setup time, and I need stuff at teardown, right?
But what I'm saying is those pieces would be external to Kubernetes, at least right now, right? They would be external things that you could do and manage on your own as an admin, and then maybe in the future.
Yeah, I mean, this is an external provisioner, so you can just take the code and do whatever you want and run it in your own cluster. Let's see. The other thing is that these cleanup methods only trigger if you set the reclaim policy to delete. If you set your reclaim policy to retain, we do not trigger these cleanup methods, and you would have to come in the normal way and manually, clean up however you see fit. But this is just, this is here mainly to automate the process a little bit more if there's like some common method that you'll use for all disks. All right, so the second feature that we're working on in 1.9 is to do some security hardening on the local provisioner. This will require some refactoring of the design. Cheng, do you want to come talk about it? You can come here. That's fine. Do you actually want? Do you want the slides that you want?
I'll just do a high-level overview of something. So one of the problems with the current design is that every single, basically a pod on every single node is going to have access to modified PVs. And we're giving that trust to basically untrusted nodes. So what we plan to do is have a centralized pod, a master that does all the PV interactions, and then have worker pods on each node to actually do the discovery and deletion. So the current design right now is to have a single master, a bunch of, I guess it's a daemon set running on every single node, probing the local volume directory for discovery. It will look at the volumes and then it will notify the master saying, okay, there are new volumes available or something has changed in the underlying system. Then master will actively create jobs for that node to actually do the discovery. And another way, as for deletion, master will also actively create a delete job, go into the node and perform the delete. So it's kind of a high-level overview. So is there anything else you want to discuss? Okay.
All right, cool. And then, yeah, so that was the security hardening. And then the last feature that we're doing or planning for 1.9 is to have volume topology aware scheduling. So this is to fix the problems where you can end up binding your volumes to nodes that the pod can't be scheduled on. Either because it doesn't evaluate the pod requirements and also because you can specify multiple claims in a pod. So like I mentioned before, these problems are seen in not just local volumes, they're also seen in zonal volumes. So we want to come up with a generic solution that will work across all persistent volumes and not just a specialized solution for local volumes. This also ties into the topology specification, where we want to be able to support arbitrary topologies in the future and not have to have specific logic to handle local constraints or zonal constraints. So the basic idea of this design is that we will delay the claim binding until a pod goes through the scheduler. And we will have some extra logic in the scheduler that will actually make the decision of which PVs to bind to. And so this is basically pulling out the decision making from the PV controller and moving the decision making into the scheduler. Then when the scheduler makes the decision, it's going to initiate the volume binding by following the pre-binding workflow for persistent volume. So it's going to set the persistent volume claim ref field and to the pod's claim, and then we will let the PV controller handle the rest of the binding transaction, where it finishes binding the claim to the volume. So we still need the PV controller to handle the rest of the persistent volume lifecycle, to handle releasing the volumes when the claim is deleted, and also handle fixing any issues with the binding if anything happens while the pod is still running. So this change may have a pretty big impact if you are using custom schedulers, controllers, or operators that use persistent volume claims, because now you might need to incorporate the binding decision into your own custom scheduler. So this is something that will break the current model. So we need to be pretty careful about when we deprecate this and make sure that we talk to everyone and make sure that they know about it and know what they need to do.
When you mean everyone, you mean users or plugin vendors or?
Whoever uses custom schedulers, controllers, or operators that also use persistent volume claims.
Custom schedulers?
Yes.
I mean, no,
If
someone said everybody. Do we really have a lot of those?
I don't know how many people out there are using custom schedulers and not the default Kubernetes scheduler. They do exist. I just am unsure about how common it is.
We might have to consider the impact of this change in the CSI proposal actually, because in that case the binding will be done by the external CSI proxy, if I'm not wrong, and we might have to consider how the flow will be in that case.
I'm not sure. I mean, there's nothing in the CSI spec or CSI implementation that impacts volume binding.
Basically, bonding is like creating the creating a PV in response to a PVC request, right? So it's like when the PV is created, the binding happens at the same time.
Yeah, but that's okay. The volume plugin can still create the volume, but it's up to the controller that issues the provisioning to handle the binding after that. But
So,
that's Kubernetes specific.
So in that case, like externally, the only thing that the plugin will do is like it will just create the PV and then it will hand over the PV and then the binding will be done inside entry or something like that.
Yeah, I think Michelle is maybe more authoritative than me, but I think this is just going to prevent the scheduler from placing a workload at a location where the binding would be unsuccessful or undesirable, right?
It's the reverse. This change is, so currently today when you create a persistent volume claim, the PV controller comes and immediately binds it to a volume. This change is going to delay the binding until we have a pod that uses the claim and it goes through the scheduler.
Yeah, basically, yeah. So this change separates binding from PV creation. That's the.
Hemant does have a point here. If CSI is assuming that the attach detach controller and provision and delete are independent controllers, then we're not going to be able to hook it into the primary scheduler like we want to. So at least for CSI, it wouldn't be able to.
I mean, we need to change the provisioning protocol to be able to
be more
wait.
explicit.
Yeah.
Yeah, we'll have to think through that.
Yeah, we'll just probably just add it to the document. We can discuss it offline.
How's this going to work for the dynamic volume creation?
It's the same thing. When we delay the dynamic provisioning until there is a pod that needs to be scheduled, and the scheduler will trigger the dynamic provisioning.
But there's nothing in the PVC that would map a PV to a pod. How would you know when you're ready, when the pod is scheduled on a node, so it's the right time to provision a volume? Like in the case of an external provisioner.
So when the pod goes through the scheduler, we look at the pod's volumes, and then we look at the pod's PVCs. And then at that time, if the PVC is unbound, we will make a binding decision. And
when you say we, you mean persistent volume controller?
No, the scheduler.
Okay.
The scheduler will make the PV binding decision, and then it will trigger the binding or the provisioning if needed.
Okay, because right now the way external provisioners work, they're completely out of the loop. They don't.
Yes.
They're not part of the scheduler. They're not part of the persistent volume controller.
So the provisioning protocol needs to be changed to handle this.
So this has a much larger impact than is estimated on the slide, because dynamic provisioners are not in the latency of container startup today.
Mm-hmm.
So there might be use cases where somebody says, create a bunch of PVCs and 2 days later come back until the storage is ready and then start the containers.
Mm-hmm.
And our expectation is that containers should start up like fairly quickly.
Yeah.
So
it is. But yeah, so this does have a lot of potential impact to the way that volumes operate today. So please think about it and comment on the proposal.
So the impact now would be limited to local volumes. It wouldn't impact
the
other type of PVs, right?
The impact right now will be limited to the alpha feature if you turn on the alpha feature.
But the alpha feature would be applicable to all types of PVs or
Yes,
just the local?
All PVs.
Wow. So then it can be very destructive.
It can.
So assuming that, all of the corner cases are ironed out, this is still going to be a big change. It's a big change to the scheduler. It's a big change to, how we consider a lot of pieces in Kubernetes. It actually raises the bar for custom schedulers. I'm kind of curious for this room and this audience. Is this, what is on the cool level from how do people feel about this feature and the benefits of it overall? Is there, okay, but binary is great. Hearing use cases and items where they feel that this will be applicable and why they think this would be, valuable to their customers and their users would be a good discussion to have too. Erin, she raised her hand with so much authority. Let me get her the mic.
Thanks. Well, it's especially useful for things like Lustre, in that, on-prem local storage, being able to actually do that instead of faking it today and perfectly assigning it and using the actual local disk is important. I know it's a disruptive change, but I think it's appropriate for a non-cloud implementation. I think Michelle mentioned that as one of her first use cases as well.
Yeah, I would say that there's a number of forms of stateful apps that they're often called cluster aware, where they have inherent fault tolerance across nodes and they want to distribute themselves into different failure domains or distribute themselves so that they don't concentrate bandwidth usage in one cluster.
So this is very high value for local storage, but very high impact for the rest of the system, because every other type of storage doesn't have affinity into nodes.
Zonal storage.
Okay.
Yeah, we have many open bugs or problems, which are basically if people are running multi-zone clusters, the pod becomes unschedulable because of the volume getting scheduled in a zone where the pod cannot be scheduled. And I think this will solve the problem. So it affects those real customers in a good way, actually.
That was going to be my question. What is the impact of not fixing this, not making this change? Are we really getting into unusable cases?
So the main thing is that we have a lot of existing issues today with zonal volumes in multi-cluster environments. So a lot of people like to spread They'll spread their pods across multiple zones. But then if we right now we just kind of randomly choose what zone to provision volumes in without considering any of the pod's requirements.
And so the issue is not with where the PV is, but really which PV the PVC is bound to.
Yeah.
Because the PVC to pod binding is, it's referenced in the pod.
Yes.
Right.
Yeah, the scheduler has accumulated more than a few non-trivial policy features over the last year, including affinity and anti-affinity, and ignoring all of those when we do PVC to PV binding seems like maybe not the right thing to do as more and more people use those functionality.
And just to add, as far as what we lose if we don't do this, right? I think Kubernetes as a platform is a platform for running all applications, right? And this is a class of applications that don't fit well into Kubernetes right now. We can sort of hack a way of getting them to run inside them, but they're sort of second-class citizens right now.
Yeah, no, so when you were asking about how cool this feature is, we see a lot of requests for something like this. My question was just about the issue we're trying to address, the delta from where we are already. And in terms of suggesting an alternative, is it the PVC to PV binding that we need to then revisit when we get into that situation versus trying not to get into the situation at all? As in, if we're using dynamic provisioning and you're picking which PV to bind the PVC to, later on you've got a stateful set or something that picks that is not able to schedule on that node. Do we then break the binding with the PVC to PV binding and then go and revisit that? But again, I'm sure we've gone through some of this discussion before.
Yeah, so I think there's two things here. Like there's dynamic provisioning and also statically created volumes. So in terms of dynamic provisioning, you could do something like, because you've provisioned it and you haven't actually used it, it's not that difficult to just like provision a new one. But we also have to handle the case where you might have, it's not dynamically provisioned and you could already have existing disks that you need to use.
Yeah, and then that's why when I think about static provisioning, I think about folks who are very well aware of what they want to do and what applications they want to land on which nodes, where maybe resource allocation or having too many, not being able to schedule the pod may not be such a big issue. But
well, generally, like the kinds of applications we want to support are going to be critical infrastructure pieces, like providing storage for the rest of the Kubernetes systems. So it is pretty important, I think, that they're going to be critical pods.
Right, but are folks who are doing the static provisioning already doing this, going through the exercise of sizing up front? So you're sizing your storage and you're doing all of that allocation. You're saying which node, which PVC. We're concerned with folks who've done that for storage, but not done that for the rest of like CPU or other stuff.
I mean, the main thing is that you will have to size your application correctly, but it's hard to scale your deployment if you have to manually have a pod spec for every node instance, right? And then whenever you add a new node or you delete a node, you have to update that pod spec or create a new one, and then you're managing 1,000 different pod specs across 1,000 nodes. So being able to integrate into stateful sets that can automatically scale up and down is pretty powerful.
Okay.
I have one question. So today when we create a PVC, we actually dynamically provision a volume, right? So that way we can claim a volume and I can use for multiple workloads. Let's say that I want to spin up one pod, does some scribbling on my PV, and then I want to start another pod. That way I have the claim on the volume. Nobody comes and hangs it out beneath me or deletes it. How is that going to work in this?
They'll still work.
Model? Because since we're delaying it, and once the pod is gone, is the claim will be gone?
No.
The claim will
The
still be
claim
there?
is still managed just like it is today. So the claim will stay, and then you have to explicitly delete the claim when you're done.
So if the claim is not bound, only then it will be bound at the time.
It will be bound when the first pod uses it. So you'll create a persistent volume claim. It won't be bound. Then you create a pod that uses the claim. And at that time, when it goes through scheduling, we'll bind it.
Okay.
And then you can kill the pod. You can start another pod. And now the claim is always bound.
Until somebody goes and deletes it. Okay. Sounds good.
I'm both glad to hear that this feature is in high demand and sad to hear this feature is in high demand. It's going to be a big one. Michelle has gone through many iterations with many folks in and out of the storage SIG to try to figure it out. I wouldn't be surprised if this one takes a little bit longer in coming. We're doing, for those of you who don't know, we're doing a lot of big surgery into the scheduler today outside of this work. I think we're like adding a whole heap data structure in order to get the starvation problem solved with priority. So there's a lot of cars moving in that spot, and it's a bit of a delicate spot. So cool, and we may have to be a bit more patient with this one. That's all, just to sort of set expectations, because this is not one we want to get wrong. The side effects are pretty big. I wouldn't be surprised if like CSI is GA possibly before this one, due to no fault of the heroic efforts of the people involved.
All right. So yeah, that being all said, there's still one kind of hole in the design that we're trying to work out. And that hole is that you can bypass the scheduler. Basically, in your pod spec, you can set the node name directly, or I think even daemon sets will bypass the scheduler. So in those cases, if you use persistent volume claims, they're not going to be bound anymore with this new design. So we need to think about some potential solutions that we can do to handle those cases. And potentially, I think after talking to the scheduler team, yeah, fixing that will be quite a bit of work in the scheduler potentially. All right. Yes. No? Okay. Let's see. So that's everything we have on our plate for 1.9. Yeah. Yeah. So it's very possible that at least this scheduling piece might not make 1.9. Maybe we'll just have a prototype or something. So. All right. So what do we have in the future? After we fixed all of those problems, there's even more things that we can do with local storage. I mean, first thing is we need to support topology-aware dynamic provisioning so that we can have a way to tell the provisioner what node or what zone to provision a volume in once the pod is scheduled. The second part of this, or another second future feature, is PV taints and tolerations. So the issue with local storage is that once your pod uses that volume, your pod always has to be scheduled to that node. If that node dies, then your pod won't be able to get scheduled. And because the use cases that we're targeting are these distributed storage systems that should be able to handle node failures, they can potentially decide, they should be able to have a way to give up on their volume and get rescheduled to a new node with a brand new disk, and then start rebuilding the data from their replicas. So that's the main motivation behind the taints and tolerations feature. After that, I guess people have said that they want this notion of an inline persistent volume, which is you can have a persistent volume that has a lifetime of a pod. I guess one of the reasons is that the root disk itself might not be big enough to store all the data you need, so you might want to use some dedicated disk. This is also not, so all of these features here are not really strictly for local storage. They're applicable to all the volume types that we have in the system. So you don't have enough root disk capacity, you can instead, provision a AWS volume and use that, or, you can use a local disk. So those are some of the other reasons why you might want why you can't use empty dir for the for ephemeral storage. And I think that is all I have here. We have documentation for our alpha implementation. There's some instructions there on how to get set up, run the provisioner, and some example stateful set examples that you can use. And then all of our work items are tracked under this spreadsheet, so you can track the status of everything as it goes in and all the different tasks that we're doing. All right, yes.
Sorry, I haven't read the specification, but in the case of a new volume, it's pretty straightforward. Basically, wherever the pod gets scheduled, you provision a volume there, and you're good to go. But let's say you want to reuse an already provisioned volume. In that case, something in your pod definition should signal that you want to schedule the pod on that node where the PV is.
Yeah, so you would just use the same PVC. So if you want to use an existing volume, you just use the same PVC.
So scheduler is going to be PVC everywhere now?
I mean, yes, it has to. It needs to look, when the scheduler looks at the pod, it looks at its PVCs, and then it dereferences it to the persistent volumes. And then it gets the node affinity on the persistent volumes to figure out what nodes it can be scheduled on.
Okay.
So correct me if I'm wrong, like the way this used to work was there's a two-step process, there's scheduling and binding. Is that right, Michelle?
Yes.
And so there were, it was kind of a two-pass complexity. And there were other items that came up because it wasn't really an atomic step when you submitted your YAML, that you would then have one moment to see the whole system and then make the decision. So in a way, there's a lot of pros and cons with this approach. Again, I'm looking at Michelle tightly, who knows this a lot more. It logically simplifies the workflow, but it makes the scheduler even more complicated and brings into more state. And because it wasn't designed this way from the outset, there are side features that really don't fit into this use case, like not using the scheduler at all, and that system not being PV aware. So it's truly making storage a first-class citizen in the scheduling functionality of Kubernetes, but we're doing it, 3 years into the project. So this is again why this one's funky. Is that right, Michelle?
Yes.
Okay. My use of the word funky, good?
Yeah.
Okay.
All right, so that's all I have on local storage. If you want to talk in more detail, I'm always available. Also, all the PR links should be in this slide deck, which I will put in the notes. And yeah, definitely we want a lot of feedback and discussion on this because it's going to change a lot. All right, thanks.
Folks want to take a quick break, or should we kick it off into snapshots? Raise your hand if you want a break. All right, let's take a 5-minute break. 2:15, we'll get started on the next topic.